Today I want to talk about torsion. Torsion is when a building is not symmetric and what happens when it's subjected to an earthquake. So I have some stuff here on the whiteboard, but I also have my little building model here. As you can see, if it's shaken in this direction, it is symmetric. The weight is over the center of each floor, roughly, and there's the same structure on both sides. If I take off one of the braces, all of a sudden there is an imbalance in the stiffness of the structure. So this difference in the stiffness causes the building to twist. Now it's really twisting. So set this aside. So up on the whiteboard here, I started out by drawing an overhead view of a building floor plan that has three different walls. I labeled them K1, K2, and K3, K representing stiffness. So if you're not familiar with stiffness, here's a concept with just a simple spring. So you have a spring and you pull it a certain amount, and then you have a resulting force. And the relationship is approximately linear, so we say that the force is equal to the stiffness times the displacement. So in this case though, with a building, we have three different displacements. We have the displacement in the x direction, the displacement in the y direction, and the displacement, the rotation actually. So rotation is another form of displacement. If you don't know what this looks like, if this overall plan view is difficult, over here I have a 3D representation. So you can see here the kind of purple, like mahogany red color, that's like the roof of the building. And the total mass, it's kind of like the mass of the roof. You don't really care about the mass of the floor below that because that's not what's affecting the structure. And then K1, 2, and 3, those are like walls. They could be braced, they could be like a shear wall, like a concrete shear wall, whatever it is. So for the one spring example, 1 degree of freedom, the way to find out the stiffness, like if you had a spring, would be to pull it a certain length and then measure the force and then divide the two, and then you'd find K. With a building, you can't really just build the building and then push it and then measure the force. So instead, what we usually do is we take a look at the model and then we say, okay, I'm gonna assume a unit displacement in the x direction, a unit displacement in the y direction, a unit rotation. And then from that, we determine the forces in the building. The forces in the x, the force in the y, and the moment due to the coupling of the forces. So I'm going to run through that right now, and then we'll see what it looks like. All right, so let's take a look at the x direction to start. So the x direction is when the building moves to the right here. So in that situation, it will be engaging wall K1 and wall K2. Wall K3, it'll be moving out of plane, but we're going to ignore any contribution that that third wall has in the x direction. So if I were to say, okay, U is equal to 1, 0, 0, meaning it's 1 in the x, 0 in the y, and 0 in the rotation direction. In that situation, the building would look like this, where you have the building had moved over 1, and moved over 1, and then it caused the wall over here and the wall over here to move, and so you're going to have a reaction force here. I'll draw that in red. You have a reaction force here equal to K2 times 1, and you'll have a reaction force here equal to K1 times 1. And then at the third wall here, you don't have anything, nothing at all. So the forces, if I were to write them out here, the forces that would be applied to the building, not the reaction. So what would balance this out in the x direction would equal K1 plus K2. In the y direction, Fy, 0. There is no force applied in the y direction when the, you don't have to apply any force in the y direction to move the building over 1 unit to the right. Moment, well, if K1 and K2 are equal and the mass is in the center and you're pushing up the center, then you're fine, it's just 0. But if not, then it's going to be, if this right here is d over 2 and this is d over 2, then it's going to be d over 2 times K2 minus K1. Basically, if K2 is larger, then you're going to have a positive moment that you're going to have to do to counteract that. So if K1 was 0, for example, then you would have to apply a torque to it as well to keep it from rotating when you push it. So that's for that part. So over here, I'm going to write down my global stiffness matrix. So we're going to have Ux here, Uy, and U theta. This right here is Fx, this is Fy, and this is M. So in the Ux column, we're going to have K1 plus K2, 0, and d over 2, K2 minus K1, like that. So that's that column of the stiffness matrix. Next, let's consider if you're pushing the building in the y direction. So if you're pushing it up that way. In that situation, you'll notice that it's only going to be engaging the third wall here, the wall on the right side. But it's going to have some eccentricity because we do not have any balanced wall on the other side. So it's going to look a little bit different. It's going to be very similar to the situation in the x direction, but let's just take a look at that. So in this case, the displacement vector would look like this: 0, 1, 0. So 0 in the x, 1 in the y, and 0 in the rotation. What that would look like graphically would be something like this. So it has moved 1 vertically, and then you have the walls right there, and right there. And these don't have any forces. The walls in the x direction don't have any force in it because it's being engaged out of plane. But this one, you're going to have a force right here equal to K3 times 1. So the resulting forces that you need to push on the building to have it have this displacement, x, 0. Force y, that's going to just be K3. And then the moment you'd have to apply, well, because when you're pushing it, it's going to be resisting there, so it's gonna want to twist this way. You're gonna need to apply a moment in the other direction, equivalent to b over 2 times K3, because that's the eccentricity here. This is b over 2. So it's going to be b over 2 times K3 to move it exactly 1 unit in the y direction. So going back to the matrix here, let's fill out for the y column, the Uy column. So we have 0 here, and then Fy, that's going to be K3. And then MB, we have b over 2 times K3. So that's that column of the global stiffness matrix for this one-story asymmetrical building. And finally, let's imagine if you wanted to impose a unit rotation on the building. So in this case, I don't want the center of the building to move to the left or to the right or up or down. I just want the building to rotate. In this case, the displacement vector would equal 0, 0, 1. So 0 in the x, 0 in the y, and 1 in the rotation direction. What that would look like, approximately, would be something like this. So it has rotated 1 radian. In this situation, you're engaging all the walls. So again, this is an exaggeration. In reality, the angles are going to be very small. So in small angle approximation, if you go some theta, and if a wall is oriented vertically here, then the distance is going to be equal to, I'll call it x, is equal to, if this is E, the eccentricity, it's going to be theta times the eccentricity. So that's going to be your displacement. So all you need to do is, since the theta is equal to 1, it's just going to be equal to the total displacement in that wall is just going to be the eccentricity, essentially. It's a little bit trickier when you're dealing with inclined walls. If it's at an angle, then you have to break it into its components. But in the case of buildings that are rectangular in nature, you don't really have to deal with that because the buildings are all in cardinal directions, so the math is really easy. So in this case, the wall right here, even though it's kind of in a weird angle, the forces, oh, there it is. So you'd have in this direction, since you're pushing it that way, it would be resisting with K1 times D over 2. And this would be resisting in this direction, K3 times B over 2. And this would be resisting in this direction, K2 times D over 2. So the forces then, so Fx would equal, well, to get it in that position, you would have D over 2 times K2 minus K1. So they're in different directions, the bottom and the top, because they're on opposite sides of the building. Fy is just going to be K3 times, or B2, B over 2 times K3. And the moment, well, it has to counteract all of that, and the forces are going to be times the eccentricity already. We have to multiply by the eccentricity again. So in that case, you get D over 2 squared times, what is that? K1 plus K2 plus, running out of room here, B over 2 squared times K3. I almost ran into my turtle down there. All right, so that's that, and then these go into the matrix here. I expanded a little bit to make room for the longer equations here. So let's see if it'll fit. D over 2, K2 minus K1, right there. And then we have B over 2 times K3. And then this one is going to be, I'll put it in brackets here so that we don't get confused. D over 2 squared times K1 plus K2 plus B over 2 squared times K3. So that is the full stiffness matrix right there. I'll zoom in a little bit. So that's what it looks like. And what this does is basically you can input any displacement into this matrix and you can get out the forces. So I'll show how that works really quick. So I'll just erase all of this. Careful with the turtle. So let's just take this displacement that's already there. If the displacement is 0, 0, 1, then the force is equal to K times U, which is equal to this whole matrix right here. So I'll just put it in square brackets here. K times 0, 0, 1. So then what you do is you take this vector here and you multiply it down this. So if you know matrix multiplication, you rotate it and you multiply each, and add up each column. So for fx, it would be 0 times this first term, the k1 plus k2. So equals 0 times k1 plus k2 plus 0 times 0 plus 1 times d over 2 k2 minus k1. And that's the first element. And the second one would be 0 times 0 plus 0 times k3 plus 1 times e over 2 times k3. So if you notice, the pattern there is that it doesn't matter where in these two columns here. It's just going to come out to 1 times this column. So really, it's just going to come out to d over 2, k1 plus k2, or minus, rather, and then d over 2, k3, and d over 2 squared, k1 plus k2, plus b over 2 squared, k3. And if you do any other combination, it's going to come out to some other value. So this is an idea of you can superimpose multiple displacements and get the total added up displacement. So this works with linear systems. It doesn't matter how many springs you have, you just add up the total effects of all the directions. Now it's really twisting.